Hello. Let's start with the webinar. So welcome to Bruker's first webinar in this year's Forensic Science series. The title is the M4 Tornado micro-XRF spectrometer, a flexible tool in forensic science. My name is Falk Reinhardt and I'm application scientist for micro-XRF at Bruker Nano Analytics in Berlin. I will be the host of this session. Before we start, let me give you some housekeeping details. You should at this time be seeing the introductory slide on your screen. This webinar is interactive. This means you can ask questions at any time during the presentation by entering your questions in the according box at the right side of your screen and sending them to us. The presentation will last 45 to 50 minutes, and after the presentation, we will address your questions. If we are not able to get to your question during this live event, we will follow up with you by email. This webinar is also being recorded, and it will be available as an on-demand version very soon. So at first, let me introduce the speakers today. My name, as I said, is Falk Reinhardt. I studied physics at the Technical University in Berlin, and I spent then 6 years as a researcher at the PTB, Germany's National Metrology Institute, where I focused on quantitative XRF at Berlin's synchrotron radiation facility. Since 8 years now, I'm working with Bruker as application scientist for micro-XRF. Our second speaker today is Roald Tagle. Roald studied analytical chemistry in Leipzig, focusing on EPMA analysis of meteorite impact residues. Later, he did his PhD on cosmogeochemistry, and since 12 years now, he's working for Bruker as application scientist. In this time, he gathered experience in many fields of application for micro-XRF. He started with the ARTAX instrument and developing an instrument, which we will be talking about today. So now let's get started. We have now a dedicated market segment management for the forensic, for the field for forensic science. This means that there is a go-to person which you can address if you have any questions in this field. And forensic, as you know, forensic science forms a key component of criminal investigations and reconstruction of other events based on physical evidence. And the data which is produced as part of a forensic investigation must, of course, be accurate, precise, and reproducible. Bruker provides analytical tools that can detect evidence long after it's no longer visible to the human eye. The instrumentation we provide covers analysis of illegal drugs, the characterization of fibers, glass fragments, paint chips, gunshot residue, and much more. Our product line makes the collection, analysis, and preservation of forensic evidence simpler by providing the ability to extract the most information from the smallest sample, while at the same time preserving the maximum amount of further tests. So there's a non-destructive analysis or very efficient tools that consume as little as possible of your sample material. The areas in which Bruker provides instrumentation listed here on the right side. So we have chemical forensic drug analysis, gunshot residue analysis, document forgery, environmental forensic, and glass analysis is a specialty. Bruker is constantly seeking to develop products capable to elevate the forensic scientist's work, and we have now a dedicated team to assist customers in the field. We clearly see our engagement in all the activities where one of our instruments is used to prevent or investigate a criminal event against nature, people, or property. Here's a quick overview of the XRF instruments which Bruker provides to assist forensic scientists. There's the handheld instruments at the very left, so which can be taken on site. There is the lab equipment, starting with the micro-XRF instruments, and there's the add-ons for the electron microscopes, several detectors. And we have the total reflection XRF instruments, so Picofox and T-Star, which have almost the detection limits of ICP-MS, but far less sample preparation need. So there's a wide range of instruments. We will be focusing on the micro-XRF part. So the M4 Tornado, the M6 Jetstream, and to a certain extent the ELU instrument. So micro-XRF is a rapid non-invasive compositional analysis. And here's a slide that should wrap up the benefits of this technique. So we need little or almost no sample preparation. You can place the sample in your instrument and then measure it. The method itself is non-destructive. So you don't alter your sample. You can use it as a pre-screening tool. So put it in, measure it, and then take it out for another, maybe more dedicated analysis. We are working with energy dispersive detectors, so we get a multi-element information. The analysis is a small spot. So you see here at the right how the bond wires are clearly resolved, even though there are 20 microns or less. The information is from within the sample. So X-rays have a certain information depth, and this IC was still kept with plastics, and we still get the signal you see. The samples can be rather large, so we measure areas much larger than 10 by 10 centimeters, or we can. And we can perform quantitative analysis, while the maintenance costs and the consumables is very low. We will be focusing on the M4 Tornado instrument. This instrument comes with, as a standard configuration, with a 30-watt microfocus rhodium tube, where the beam is guided onto a spot of less than 20 micrometer diameter. What will be topic of this webinar is that other anode materials are available. So if there is some applicative need, we can provide other anode materials. Optionally, a second tube can be attached. This will then be a collimated tube, not a second lens. Up to 2 silicon drift detectors can be attached, so with either 30 or 60 square millimeter active area. And these detectors have individual pulse processing units, and you can get really twice as much counts with the second detector. The sample chamber is vacuum tight, so we measure at atmospheres as low as 1 millibar. Usually 2 or 20 millibar is the standard conditions. And thus we can detect light elements down to sodium, and with the light element windows of the M4 Tornado plus even carbon. The sample stage is motorized, and with a rather large measurable area of 200 by 160 millimeters. The sample can be 12 centimeters high and up to 7 kilo of weight, kilogram. And the sample stage moves rather fast with 100 millimeters per second, and the minimum step size is 4 micrometers. And after this introduction, we can now start with the webinar.
Okay. Thank you very much for the nice introduction, Park, and welcome to the webinar on forensic science and micro-XRF. So, as I have been seen from the list of participants, many of you are familiar with the work of forensic, and we will try to discuss a little bit the potentials that we see, that we try to identify in our machine, and trying to illustrate those for the field, especially of forensic science. So we will be briefly going over several topics until we get to the last one, which will be a little bit like the most of the time of this presentation, which will be fingerprints. So first we will start with gunshot residues, and especially when we talk about gunshot residues, it's really a shooting distance determination, even if some particle analysis can be done with a micro-XRF, but it's not the typical SEM work of gunshot residue, which is referred in this case. Provenance analysis of soil is something that we will just briefly discuss, as well as the possibilities of the instrument to study modern art historical document forgery, how to analyze the ink and how the ink is deposited on the material. And last but not least of this introduction part, where we talk a little bit about the glass shards and identification of representative materials and glass shards. Before we go to what we will consider in this part of this series of forensic presentations, the major part of this talk is fingerprints. So in the part of fingerprints, we have a little bit more topics that we would like to discuss and present to you. Okay, so starting first with gunshot residue. Some of you maybe have seen already our presentation in this direction. We have done several works already presenting the gunshot residues potentials of the M4. There are also several publications, including the use of the M4 in the field of forensic science, especially for the gunshot and shooting distance determination, not only for the M4 Tornado, but some of these also include the possibilities and potentials of the M6 jet stream for very large samples and large area scanning. Yeah, so basically here it's a little bit, even if it's called gunshot residue and we're really discussing about gunshot residue, we're not looking in the principle to the detail of the small particles, but with the machine and with the system, we're able to really study relatively large areas in relatively short time and get a very nice intensity distant correlation and trying to figure out what was the distance of the shooting. But I would recommend you, if you're interested, either contact us or research on the publications by forensic specialists and the experience they describe in their work.
Yeah, the next topic is about environmental forensics, so yeah, provenance analysis of soils in this case. Here, yeah, the topic is that if soils are found on a crime scene or a place of interest, they can be sampled. And in this case, as you see at the bottom left, they have been sieved to a certain size fraction and then put on an SEM stub. They can be mapped then with a micro-XRF instrument. And based on the phase analysis, we get a fingerprint of these soils. So the ratios of different particle sizes are different mineral phases in this soil.
Yeah, the nice thing is that the M4 Tornado allows it gives the possibility of when collecting the data per pixel you acquire the full spectra. The software includes several tools for data evaluation or so-called data mining, which allows to identify regions with similar spectra and group them after deciding to, let's say, what type of mineral you might be finding. For example, it's here relatively simple in iron-rich minerals or potassium feldspar or silicon-rich, which might be most likely be quartz, calcium rich at the moment without any further identification. You could also be able to identify, let's say, minerals like, yeah, zircons and the amount of minerals, relative amount of certain minerals compared to others. And you also have the possibility to get quite reliable quantification, let's say, for the different types of potassium and calcium feldspar that you find in the location. So not only to sort them in terms of this is a feldspar, this is a potassium feldspar, this is a calcium feldspar, but you can really quantify them quite reliable. We have done already webinars where we show how to quantify even small particles, and in the next coming webinars we will discuss a little bit more in detail about the possibility of quantifying small grains and how can you really not only say this is the relative amount, but also give them some kind of information of, yeah, the feldspar I am finding here are within these range, let's say, of the anotite, albite, or microclean range.
Now, a short introduction to modern and historical document fraud, how micro-XRF can support here. So the M4 Tornado allows for the elemental scanning of materials, which are used in the creation of modern and historic documents. And yeah, based on the composition of the inks, for example, or the paper which is found, you can learn the provenance of these or the time of production. And yeah, nowadays maybe some manufacturers have unique compositions of inks which can be then traced back based on the measured composition. We have here on as a sample a sheet of paper where with 3 different pens, a gel pen, roller ball, and ballpoint pen, we have drawn lines, or lines were drawn, and yeah, so we can scan this piece of paper and do an elemental analysis. In order to minimize the background, we elevated this piece of paper slightly above the base by putting it on a mylar foil and in a box which is roughly 8 centimeters high. So we get much less scattering from our acrylic table, or in this case, the bottom of the box, and therewith a better signal to background ratio. So what you see here is the scan of the sheet of paper and a display of how sulfur and copper are distributed on the sample. So yeah, marker elements for the different inks. So of course, with this micro-XRF, you get an elemental information on your inks.
Additionally to the possibilities of the instrument to, let's say, give you a spectroscopical or an elemental information about the material, what you basically see on the top right image, where the stronger sulfur signal is characterized by the stronger yellow color, or the copper are characterized by the strong blue color, are defined. So we have also some additional information. It is how the ink and how the material interact with the with the paper or the material in which is useful. For example, here we see very apparently typical for this material, that when the ink of the gel pen is applied to this paper, we get a distribution of some elements in different distance. That means how deep into or how far the migration of the different components of the ink might be distributing into the material. This analysis of modern and historical documents using micro-XRF has been done already also in the field of art and conservation. For example, the analysis of the magic flute from Mozart, and we have been also really directly involved in the analysis of Da Vinci, and also a lot of very interesting documents and manuscript in which is possible to identify what type of material was used for creating this one, and even some of them where it's a discussion of if it's original or not. So many of these kind of applications can be addressed directly by the use of micro-XRF. So here, for example, once we know that we have here three different typical materials, we can identify them. Let's say one seems to be characterized by more enrichment in zinc, where the other ones are more typically for a sulfur and a copper enrichment. Basically, once we can cut the data, let's say you see the green objects on the top of each of these areas of interest, and then at the bottom we see the cut spectra. So basically we can really identify and really detect that let's say apparently more copper is really related to a higher amount of copper photons in this area. And based on that, so a direct quantification is not possible. We're not talking about a perfectly, let's say, infinitely thick or ideal sample, but we can create very nice element ratios and really get also numerical classification or possibilities to differentiate different types of material by element ratios.
Yeah. So the next quick introduction will be to the forensic particle analysis, specifically to glass analysis. We already discussed this in a webinar about forensic analysis. There is even an ASTM norm to do this, to classify glass shards for forensic analysis using micro-XRF. The main problem also addressed there is that these particles are small. So, and while micro-XRF usually has no problem to hit the particles, so they are usually larger than 20 micrometers in size, we might be running into problems with the thickness of the particles. So both the quantification as well as the net peak intensities, which can be used for classification, need a certain thickness of the sample in order to be representative for the sample. And this is a problem since X-rays can pass through material. So glass is not only transparent, small glass is not only transparent to the visible light, but also to X-rays. And if these samples get too thin, our quantification algorithm, as well as the net peak intensities, will be giving wrong values. So the question will always be which particles can be quantified and which are too small. And this is a pretty straightforward process. So first step is to validate whether the quantification can be used at all. So you need a standard to verify that it works. Then in a second step, you take a reference sample which you have no problems to destroy, and then you produce a lot of small tiny glass pieces of different size and assess the size range for which this is possible. This is especially interesting for glass and aluminum particles because those are pretty light matrix but have heavy elements which are needed to properly characterize the particles.
Yeah, basically, we will just briefly go about the glass part in this presentation. The other ones will be including a little bit more detail for other types of material. So basically, then the ASTM norm goes for or suggests the use of element ratios, as these are more reliable, especially for the small particles. What we're showing here is a little bit like first starting with a validation of the procedure. So the M4 Tornado comes with a fundamental parameter quantification. That means you don't require reference materials to quantify a sample. You see, for example, the results of analysis of a reference material NIST 1831. And basically, you see the results at the top. And if you compare that to the expected values, we see, for example, that the magnesium values are a little bit lower than expected. Here for M4 Tornado, and the software allows the opportunity or gives the possibility to easily create a standard supported fundamental parameter quantification where you can attach, let's say, or adjust a fundamental parameter quantification by using one or even more reference materials and optimize the results so that you get then the expected values. In this case, the type calibration factor for magnesium was 1.06. This is you enter in the software, and after that, the results of the quantification are, quite good. So basically, we did this first identification of the, or let's say validation of the method sorting for a known reference materials. Then we look at the material that we want to try to figure out if the particles are representative to the large sample of glass. Like here is again still a validation, but this is the reference or the compare glass, and we're at the moment just working with composition. You see that our values are in very good agreement with the expected values for the reference glass to look at, and yeah, basically the composition values are very reliable. And then we can go from now, these are the expected values from the glass, to the little tiny particles, and try to discuss a little bit different approaches for how to measure these tiny particles. So
yeah, and that's why we have here a mapping again. So you see many different glass shards of this reference glass, and yeah, they were mapped in one run. And then into this data block, we can draw objects which try to reproduce the shape of the objects or representative part of the object. So this is a very important part because from looking at those glass parts, you do not know which one are really large. You only know the X and Y dimension, but not the Z. So you can have a very large piece, which is actually very thin, whereas a smaller looking particle is maybe even thicker. And yeah, so if you do a mapping, you will be seeing where you have the representative part of the sample in these large areas. For these large samples, most of the sample areas representative.
yeah, basically there is a lot of discussion always what is better, doing a point analysis, then you have easy possibilities to achieve a lot of statistic. Do you need to take care about the distance? We will discuss that in our next webinar again. I'm sorry for this one, but just to give you a short discussion about that, you don't need really to take care about really focusing the sample. The differences between being in focus and just few micrometers away on the intensity are negligible. So basically, the main advantage of the approach of area scan is that, for example, you would recognize the third dimension of your particles that you basically will not see from a microscope looking from the top. Also, the possibility to exclude contaminations of your sample is something that needs to be taken into consideration, because especially, let's say, if you have a float glass, some of the areas or surface that you will be looking at might be containing the tin coming from the float area, but you're not sure. If you don't do an elemental distribution and you see that the tin is not distributed homogeneous or any contamination is not distributed homogeneous. So the main advantage, and that's something that I'd like to focus on emphasis of the using a scanning device, is that you have the possibility to identify the representative areas of samples that might be not homogeneous. Just doing a point analysis requires to accept or goes from the starting, let's say, precondition that this point is representative for the other part of the sample that I'm not measuring, and this is also always only an assumption. So basically now we just did the same more or less. The first one were relatively particles in the millimeter, sub-millimeter range. Now what happened when my particles become smaller? And here we would like to discuss a little bit what happened with time, acquisition time and small particles, and how these might be influencing a little bit my identification. And yeah, you see the measurement time here. The scan was done, the overall time was 25 minutes. The acquisition time per pixel was 10 milliseconds. And it was a total number of 65,470 single points in this elemental distribution. Basically, from here on, we can, similar to what we did before with the larger object, cut objects of my sample, and these will be added by the software together to 1 pixel. And as you see here, these pixels, some of them you see short 1, 2, and 3 labeled already. On the right side, you see the representing measurement time behind each of these objects. And as you can really see, for example, especially the short number 2, with approximately 2 seconds of real time and 1.7 seconds acquisition time, is relatively short measurement time. And if you compare, for example, the element ratios, and element ratios comparison is more, let's say, reliable in the terms for small particles, and it's also what is recommended in the ASTM norm. So you see that the objects, especially the large fragments, are very good representing the composition of my reference sample, where the small fragments, some of them you see the triangles, are a little bit farther away from my area of interest. So I have a little bit of, the small particles are not reliable for this identification, and the main problem for this one is that the measurement time is not sufficient. So basically, the validation in this case, it fails because we have too short time. So you should consider, when you do an area scan different to a point analysis, that you accumulate for the amount of time that you previously defined as required for this kind of work. So basically, point analysis is one option. Scanning is the one that we would recommend, as we have the possibility to identify non-homogeneous sample. And now, about talking about scanning, we will go to another material where scanning is more likely the way to go.
Yeah, and this will be the fingerprint characterization. So the visualization of fingerprints by micro-XRF is nothing we invented just now. It has first been described in 2006 by a group in Los Alamos National Laboratories. And yeah, the approach is based on detecting the inorganic components, so potassium, calcium, sulfur, and chlorine. This has the advantage that it's not hampered by dark or multicolor background, which may be a problem if you do some contrast enhancing in a traditional way. It also is not, it does need the organic parts, so it doesn't have to be sticky. It doesn't rely on sebum or other organics. And nowadays, with 15 years of technological advances, this technique is now, it's getting better and better. So you can record more data in shorter times. And with this, really try to visualize these residual fingerprints. So most common X-ray tubes usually, also there used to be the molybdenum tubes. Nowadays, rhodium is more common, but neither of them are perfect for this kind of analysis, as we will be showing, because especially the chlorine is here a problem. The overlap of rhodium with chlorine is significant, and this makes it sometimes difficult to detect low amounts. We addressed this in a webinar on concrete, where chlorine is usually a very element of interest, and therefore, we already showed some differences between those two anode materials. And what we did. So first, micro-XRF is also a contrast enhancing method. Here we need an elemental contrast. So if there's an element in the fingerprint which is not in the substrate, we have get high contrast. And if the element is also in the substrate, and then the contrast gets less. But this, the substrates which are conventionally challenging, like leather, plastic, skin, some textiles, or even some papers, they are not that much a problem for micro-XRF analysis, because we are looking for something different here. And since micro-XRF is detecting non-volatile inorganic components, it should be able to detect fingerprints which are much older than the usual ones, or have been altered, or maybe not altered, but yeah, subject to environmental influences to a certain extent. And
yeah, so basically the idea of in preparation of this webinar, we thought about how to create some kind of small experiments in order to first try to illustrate and learn a little bit more about detecting fingerprints and what happen if we try to destroy or try to some kind of alter original fingerprint on surface. In order to simplify, we use a quartz disk, and basically we took two types of fingerprints, one more in the greasy side and the other one more, let's say, sweaty fingerprint. And we exposed these two types of fingerprint. We measured that several times, and so we exposed them to different conditions. So we exposed the set number 2 to a heating at a temperature of 500 degrees, and the second one, we also, the number 3, we heat up to 250 degrees. And this one we also coated with carbon, using the normal laboratory carbon coater as you use for the SEM analysis. So basically this is the treatment that we did, and you see, for example, here our heating setting, and you see how the disk was looking after several hours of sitting on on a plate with a temperature of 500 degrees. So it was really carbonatized, and it was really looking very different than expected. Now we would like to see, and the idea is, how does, first, can we detect the fingerprint in the original way? What are the potentials, and how does it look like if we just try to change this or kind of destroy them? So basically from the experiment, we see here the fingerprint, the greasy on the left side. On the right side, we see the sweaty set of fingerprints. And this was the first quick scan in order to get an idea of if we see that this is an untreated sample, original, so that we have 3 set of more or less identical to start with. And what we see here is very characteristic. So the greasy fingerprint barely has any signal for sodium, potassium, or calcium, where there is some signal for chlorine that can be detected in the greasy fingerprints. And in case, for example, of the sweaty fingerprint, we see signals for all 4 elements. So interesting, the chlorine seems to be, especially for more the greasy part of the fingerprint, a quite good, contrast element, as was presented or said before by Falk. So basically, it's an element that gives a quite strong contrast, because its contrast is mainly it has 2 factors. One is the amount of these elements in my sample with respect to the surrounding, and the other one, which we need to take into consideration, is also the sensitivity of the instrument and the setting to my measurement. So as you see here now, once we already know that we are able to detect that, we will now focus first on the sweaty fingerprints and how to improve the, let's say, the contrast. Here we did a longer measurement time, so this is an overnight scan of the same sample that was previously measured for 1 hour. And what you see here is that we improved the contrast. So basically, since now we have a better statistic, we start seeing some fingerprint for sodium, and we have improved considerably the result for potassium and chlorine, and also for calcium. However, the contrast is much better in this case from what we can see here for the elements potassium and chlorine. If we just grab 2 of these fingerprints and, let's say, display, and we just plot the potassium and the chlorine fingerprint elemental distribution contrast, this is really just elemental distribution. Behind these image, you got just an intensity matrix of these 2 areas, or for these 2 elements. And if we compare, for example, in order to get a feeling about how strong is the contrast between the glass and my fingerprints, you see that on the spectrum at the left side. So basically, you see the silicon peak for the quartz disk, and in top of that, you see the contribution of the contrast element, and you see there's a quite strong, the strongest peak are basically the potassium and the chlorine peak, and you have a small peak for calcium and a very smaller even for sodium. But basically, this is the element sensitivity contrast that we can achieve with the machine for this kind of application. Okay, so basically we saw first that there is no problem. It seems to be quite possible to detect and visualize the elemental distribution on the fingerprint. Now we will try to see what happens if we start, let's say, altering the fingerprint by the different things that we were discussing before, like heating and coating and all of that one. So now, before we show you, what we will try to change a little bit the way we're displaying the results. On the top of these two images, you get exactly, it's the same data. So the same data is on the top, but in a contrast going from white to dark. Let's say the fingerprint high intensity is in this case given in black. The bottom one is different, it's the opposite of these one. And I would like to get this kind of change in color scale, because here with the option of black and white but opposite, we have more possibilities to change and adapt our contrast and background to optimize the visualization of the fingerprint. So basically it's the same data, everything is the same as we were showing before, we're just changing in the way that we're visualizing the fingerprint. So, and now you see the results of our experiment. Remember what we were saying before. So the first measurement at the top, sample 1, 2, and 3, untreated, original. Second measurement at the bottom. So first, keep untreated, original. Second, heat up 500 degrees for 5 hours. Third sample, heated up to 250 degrees for 5 hours and coated with the carbon coater of the SEM. And basically, even I mean, we are not really experts in terms of fingerprint, but if you take a look at the images, and basically the measurement time was the same per pixel, just the area is a little bit larger, so that's why one was a little bit longer measurement time than the other. But basically the acquisition time per pixel is exactly the same in both measurements. And you see here that we're, especially the sample treated to 500 degrees, is very strong. The image quality, I mean, you can see it's a fingerprint, you can identify some of the structures, but it is really very strong decay of the fingerprint quality. In case of the 250, we were not really seeing any significant changes on the fingerprint quality, neither by the heating nor after the coating. So basically, apparently, and let's say this is just basics experiment, it's not intended to be a, let's say, a proof or a fully validation of the procedure of survival probabilities of fingerprint, but it seems to be an indication that fingerprints tend to be decaying depending on the high temperature. The higher the temperature, there seems to be some process that tend to eliminate, or let's say destroy a little bit the information of a fingerprint. However, heating up in our setting under the given condition 250 didn't do any significant change to the fingerprint, and that's what we wanted to just, beside of showing the possibility of instrument to present the fingerprint, just to look a little bit more at what are the possibilities on the situations that you might not be able under conventional settings to get good fingerprint results. And
just one thing I wanted to mention, the measurement conditions for both measurements have been exactly the same. Only one area was a little larger to measure. That's why it took 3 hours longer. So here you see more quantitative means of comparing the silver and rhodium anode as means for detecting chlorine in a sample. So we have a spectrum of a different NIST reference material. It's NIST 620 soda lime glass. And so there's a comparison of the detected count rates in this with these two systems where the measurement conditions were exactly the same. So, and here we see that for most of the elements, the count rates are pretty much are very similar, and only for sulfur and then chlorine we have really big differences because they are first the sulfur, because it's slightly differently excited, and for the chlorine we have the problem that with the rhodium tube we don't even see it. So it's also not really certified component of the NIST glass, so there is only traces there. But with a silver anode, we do see that there is a little chlorine peak, which we cannot detect with a rhodium instrument. If we have amounts of chlorine which are really detectable, we do detect it with a rhodium tube. We can deconvolve this, but this qualitative approach, we have a much better contrast with the silver tubes.
So basically, in principle, it doesn't mean that it's impossible to detect this chlorine, but in this case, you would need a filter to eliminate the primary radiation of the rhodium L line, and this will be diminish a lot the sensitivity, additionally the sensitivity of the instrument for the chlorine. So you would require a much larger, or much higher counting time, and still your limits of detection will be much higher. So you will not be as good as you are with a silver, which has two advantages. One, not overlapping, and second, sitting in the sweet spot of the excitation edge of the element chlorine. So basically, the fact that the silver tube is more sensitive for detecting chlorine and allows us, for example, in this case, it's a paper. This is a non-intended fingerprint on a paper. Basically, the same measurement condition, one with a silver anode and the other one with a rhodium anode. And what you see here exactly, very similar to what we were showing and discussing before, is that in the left side where you have the silver anode elemental distribution for chlorine, there is a very, very clear signature, at least of one fingerprint, and some traces of another one, where in the right side, which is a rhodium image or elemental distribution of the same area, now that you know where to look at, you have the feeling that you can see some lines there, but if you would not have these one to guide, it's very, very difficult to get a significant contrast to identify the fingerprint in the second one. So basically, the silver anode, it's really helping a lot to identify the chlorine and get a good contrast for these elements on a sample.
Yeah, and with that, we start to summarize our findings on the residual fingerprint analysis. So in the spatials as well as the sweaty fingerprints, it was well possible to visualize the friction ridges with the micro-XRF, especially for the element chlorine. And in these sweaty fingerprints, all main marker elements, so which we consider the main marker elements, so sodium, potassium, calcium, and chlorine can be detected, and these spacious fingerprints had only the chlorine for us to detect. And since chlorine is abundant in both these types of fingerprints, we would suggest a silver anode for if the specific application be the detection of fingerprints. The small set. So we did a short experiment with a small set of samples where we did which we altered in different ways. So the heating to 250 degrees seems to have no significant effect on the fingerprints, whereas the 500 degrees was too much for the one fingerprint we tested. We also didn't find no effect on recovering a fingerprint which has been covered with carbon. We expect this carbon to be like 50 nanometers in thickness. And here on the right side, you have a graph how much chlorine signal you could detect through different thicknesses of pure carbon covering the sample. So if you have 25 micrometers of carbon, which is a thick plastic foil, you should be still seeing 50% of the chlorine intensity. If you have 100 micrometers of carbon, so that's a lot of carbon, you could still detect 5% of the original intensity. So even under very thick layers of, for example, soot or differently covered, you should be able to detect the chlorine. And in some fingerprints where you have the potassium or the calcium, you can even go through thicker layers of this carbon. And
yeah, basically now we're coming a little bit to the end and starting soon with our Q&A session. But before that one, I just want to give a briefly outlook of this webinar. We present a little bit of what we can do or what we are doing with when we are talking about GSR with micro-XRF. We discuss a little bit about the potentials of the provenance of soil, ink analysis, glass classification, and focus a little bit more into fingerprint residuals, illustrating a little bit the advantages or potentials of a silver tube for the identification and visualization of fingerprint compared to standard instrument with a rhodium or molybdenum tube. While focusing on fingerprints here, we are planning to have a series of webinars, and we invite you please to join us to these webinars. Also, if you have questions which you would like to get addressed in these webinars, please don't hesitate to ask us these questions. So we might be even trying some small experiments, trying to really figure out what are the potentials and limitations of these techniques, and really present these in the frame of a webinar. And by saying this, please, I open the session for the Q&A.
Yeah. So, yeah, thank you, Walt, for until now. We had some questions coming in, but first let me quickly point out, so I said that we have now a dedicated person to address the needs of the forensic market, and here's his email address. So Michele Giordanda is our market segment manager, and so if you have questions, you can contact him. Yeah, so there have been questions, and I wanted, for example, in reference to the glass fragment analysis, does the surface orientation change the quantitative results or the confidence in the results?
Basically, for a quantification, it depends how strong the misorientation to the flat of the system is. If we're talking about 1, 2, 3, 5 degrees, it changes, but it depends how relevant you can consider that one. So if it's a strong deviation, let's say 30, 40 degrees, you would really see that on your non-normal, especially on the non-normalized totals, because you might be tilted towards the detector or away of the detector. So both directions are at least possible in an extreme case. But the small particles that we're discussing here usually are more or less randomly distributing all of the areas. And you should not try. And basically, if you take a look at the images of the glass particles, you would see what of the areas are more or less to the shadow. And these areas that looks like being in shadow are for sure giving less intensity to the detector. Basically, yes, it will affect the quantitative results, but the effects on the element ratios will be much more or less than these, because they will be quite similar especially if the elements are close to each other, which means the lines have a similar absorption and emission physics behind themselves. So basically, that's why the ASTM norm does not suggest to use so much the quantification, but the element ratio, which are less susceptible to this kind of effect.
Yeah. And in this case, we are lucky that our X-rays do get into the sample. So on the one hand, it's a problem for measuring thin samples. On the other hand, it's good because then we have less. So the surface to volume effects are less pronounced because we have more volume than, for example, the SEM analysis. Another question, maybe we didn't make this clear enough. So we showed the firearm discharge patterns, and we pointed out copper, barium, and lead as the elements. And the question is whether our instrument can detect in this discharge pattern also other elements. So in the analysis of these. So let me scroll back for everyone to have this visible. And yeah, so we only in this case showed these 3 elements, but since we are using energy dispersive detectors and also with this hyper maps functionalities, we do have the whole spectra for all these elements, and our spectra usually go from 0 to 40 keV. So all the elements which are in this spectral range, and these are pretty much all the elements from sodium on, can be displayed.
So basically, after you save the data, any element that was detectable at the time of the measurement under the given condition can be displayed after the measurement. So you do not rely on your pre-selection of elements of interest, but let's say after the measurement and data evaluation comes to, let's say, to the mind that will be interested to look, for example, for antimony in the material, and you didn't look previously to that in your evaluation, it will be in the data if it was detectable on the measurement settings that were used to analyze these samples. So it's everything in there that was detectable recorded in the file.
Yeah, and another question which is somewhat related to this. So we mentioned that we can map 19 by 16 centimeters, and there is a question of how much time it takes. And there's no definite answer to this one because it also depends on the step size you choose and also the measurement time per pixel. So you have here two examples. One is 9 by 9 centimeters, which was measured for 5 hours, basically, or primarily to create this very nice picture. And then we have this up here on the right, 14 by 14 centimeters measurement, which took 3 hours to measure because we had either larger step sizes and or lower measurement times per pixel. So this is freely choosable by the operator.
Yeah, in principle, the measurement conditions may be changing a lot the total acquisition time. That's not a fix. In principle, it depends a lot of the application. If you're looking, for example, a major element, just a short measurement of let's say, few minutes, depending of the area that you're looking at, may be enough. In case you're looking at trace element and very, very small variations, you might require longer measurement times, let's say an overnight measurement or even a weekend measurement. But let's say in the area of the gunshot, for example, that we're showing there, we can cover and get very similar results within an hour or less. But you will not have the high resolution, you will not have the high good contrast, but in principle, you will be able to see the enrichment and all of that one. It depends a lot, as I was saying before, from the analytical question, how long it takes to get, how long the measurement might take.
All right. Yeah. Another question is, what is the spatial resolution limits? Is the spot size of 20 micrometers the minimum area which we can focus on? And so there's two steps to this. So the minimum step size of the instrument is 4 micrometers. So this is the smallest you can have the stage running. This measurement point is usually below 20 micrometers and slightly energy dependent. So for lighter elements, you have larger spots than for heavy elements. And there's also all the physics behind or which come after the X-rays hit the sample. So there is scattering and there is the information depth, and these also do limit the spatial resolution. We had a webinar last year where we talked about optimizing measurement conditions for mapping display. And in this, we also showed measurement series on how the sample thickness defines the minimum spot size you can achieve much more than significantly. So if you have a sample which is 50 micrometers thick, you have a limit to the spot size which is not based on the quality of your lens.
So basically, spot size and maximum resolution depends not only on the spot size of your instrument, but also on the material you are analyzing. So basically, it's a combination of these two things, what are the maximum resolution you can achieve with the instrument. I think there was I saw one question, was something we were probably not very clear with that one. The samples were not heated inside of the M4, so we have no probability to heat samples inside of the machine, but the samples were heated outside. So basically, we use a conventional lab heating plate, and you saw the picture at the beginning. So basically, we use this plate to preheat the sample and look what are the effects after the heating zone.
Yeah. So the question was maybe the sound quality with this webinar is not perfect. Whether temperature changed the ratios in the glass analysis. I think tilting and temperature was maybe mixed up. So we didn't. The temperature usually has no effect on the X-ray characteristics of a sample. So this need to be extreme temperatures to have effect. We don't have that. So no, heating a sample prior to measurement may have an effect, but inside our instrument, there will be no changes due to temperature. we have a question here again regarding the glass characterization. When comparing an unknown glass sample with a reference, would you advise to compare the element ratios rather than the quantitative results?
Yeah, basically, this is also stated in the ASTM norm for micro-XRF forensic analysis of glass, and we fully agree with these. And basically, they are the main reason for that. I mean, you can use the comparison of the quantitative results, but these will be always be dependent on having a perfect, let's say, yeah, identical, let's say, infinitely thick homogeneous sample. And any effects of gray of particle size, for example, in case of the small glass shards, will be changing your element ratio. And here it's not only important to consider that element ratios are more reliable for the comparison than full quantification, but also the elements you are using for this comparison are relevant. So we we will focus this one a little bit in the next webinars. Basically, one thing important for you to take home message is that in micro-XRF, information depth is really important. So information depth for a given material depends on the energy, so depending on the line. So if I'm looking at potassium, which is very close to calcium, the ratios of these two elements suffer more or less the same physics of emission and absorption. If I'm looking at strontium, which is a 15 kilo electron volt, they suffer completely different intensity in absorption and emission effects. So if for small particles, I cannot compare the calcium to strontium ratio, these will be not stable. And basically what you have is, in depending of the size of the particle you are analyzing, there is a limit until which element or which energy can be used to get a ratio with lower elements. So the comparison of the elements, yes, it's more reliable than the quantitative analysis, but same as a quantitative, you need to be ensuring what kind of elements you are comparing. The best is to compare elements that are close to each other, and to consider in which elements to compare the size of the analyzed sample.
Yeah, and there's also now a question on the different anode materials, how important they are. Yeah, so in principle, so we here pointed out that a silver anode may be, or yeah, seems to be more suited for analyzing fingerprints. Still, we have the rhodium anode as the standard anode material because, especially in the geological applications, this is a very, yeah, the best suited anode materials. Has a very efficient excitation for all the elements up to molybdenum, and the physical effect of Compton scattering, which is a problem in the high energy range, overlaps only with elements technetium and ruthenium, which are very rarely found in geological samples. And so for most applications, we consider rhodium the universal tube material, and we suggest sometimes other anode materials if specific applications call for this.
Yeah, especially the main disadvantages of silver is when you're going to quantify silver alloys. So basically this makes the machine a little bit, it's not impossible, but it's a little bit more difficult to handle. So same with the rhodium, but usually people are less daily analyzing rhodium than silver might be a possible application. That's one of the main reasons why silver has let's say rhodium has become a more standard type of anode. And basically our idea of changing from the standard rhodium to silver was when we start to become all of these questions regarding the sensitivity of the chlorine for the building material analysis. And now we just see the potentials also of these changes on the anode for the analysis of fingerprint, because we are able to visualize one which seems to be the most relevant element for fingerprinting at the moment from what we see, which is the chlorine. And basically it's a kind of trying to optimize the machine and the analytical possibilities, and compromising, let's say, a little bit of the possibilities of quantifying or easy quantification of silver alloys so far.
Yeah. So another question is whether we have any experience in applying XRF to paint analysis, so maybe car paints, something like this. And
yeah, basically the analysis of sometimes, so we have done some analysis in the field of micro-XRF, for example, analyzing chips of car paint. The main problem here is that the layers are really, really thin, and we're starting to get close to the point that in terms of excitation and analyze volume, the beams start to get, let's say, a mixed analysis between the different layers. So here, we are sure as a main advantages of micro-XRF, we can detect the trace element in the different layers of paint, but we have the problem that because the paint layers are very, very thin, we don't know exactly where they are situated. So here, the spatial resolution, because the paint layers might be in the sub-micrometer or let's say micrometer range, we will not get them separated from each other in the collected data.
yeah.
So basically it's possible, but the amount of let's say you get all the, or several of these layers mixed together. Nonetheless, there's some researchers, forensic researchers, using this one also to characterize paint layers.
Yeah, we ourselves do not have many samples on that matter, so therefore we cannot give or make some small experiments. We might be finding some. So maybe in one of the next webinars we give at least a brief glance on what we find on that topic. I think with this, our time ran out. We have some additional questions and also suggestions for future webinar topics. So I think we will be getting to the questions which we didn't address in this webinar per email. The webinar, as I stated, has been recorded. So if you want to have a look at it later on, you can watch the video, and also the slides will be for yours to review. With that, I would say thank you, Roald, for your contributions, and you for your attention. And yeah, goodbye.